I'm Anil Kumar, and in this video we'll get the concept for critical numbers and its relation with local maximum and minimum. So whenever we talk about critical numbers, we are looking for numbers in the domain of the function where the first derivative is either 0 or is undefined. So this is what we are looking for. That really means that if I sketch a function, we could find this from a sketch or even from the equation. If I have a graph, let us say the function's graph is kind of like this. So this is what we have drawn here is a function, right? So what you notice here is that the slope will be 0 here. So that becomes the critical number, right? Or we could have a situation where the graph could be kind of with a cusp, right? Could be kind of like a cusp here. In this case, at this point, it is the critical number, since here the first derivative is not defined, right? So you could say if you draw a tangent at this point, then it is a vertical line. Do you see that? A vertical line. So in both the cases, we do have critical numbers, and in the first case, we have two critical numbers. One, let me call this as C1, the other one as C2. Here we have one critical number, which is because the derivative here is, here in this case, f dash as c is not defined, as we say undefined. And in this particular case, f dash as c is 0. So in both the cases, whenever you get first derivative as 0 or undefined, we call them critical numbers. Now, the second point which you need to understand is that at critical point, derivative is either 0 or undefined, which we have already considered, right? So critical number is in the domain of the function. So it has to be in the domain where the derivative is 0 or undefined. So these are kind of same lines, but we are using two different terms. At times we use critical number C, at times we use critical point P, for example. So that becomes a critical point, this becomes a critical point, right? So we could use either of these terms, but the idea is at critical point, derivative is either 0 or undefined. Okay. Now, another part of this understanding is that at critical point, local maxima or minima may occur. So this is kind of very important, may occur. In these two examples, we have a local maximum and a local minimum. In this case, it is local maxima, right? And here we have local minima at the critical point. In this case, this is local minima, right? But there could be cases where we may have derivative as 0, but we may not have that point or the critical point as a local maxima or minimum. Let me give you an example. Example is kind of a cubic function, right? If I draw a cubic function, let's say like this, in that case, what you observe is that we do have a critical point. So this is a critical point C. Since at this point, the derivative is 0, right? So the horizontal line is a derivative at this point. However, at this point, we do not have local maxima or a minimum. You see, it doesn't really turn at this point, right? So it just keeps moving away, right? So that is what it is. So at critical point, we may or may not have a maxima or a minimum. So that is kind of important to understand. Now the question is how to find, right? How to find that we do have a maxima or a minimum or not. So how to find or verify that we do have a maxima or a minimum or not, right? That is a very, very important question. So the way to find is to check for the derivative on either side of critical point, right? So for that, let me take algebraic equation. So we'll say a function f of x. So let's say this function is cubic function. So let me write this as x cube. in that case derivative of this function will be equals to 3x squared. So which is 0 at x equals to 0, right? So we know f dash of 0 is equals to 0. So that implies that we have a critical number, right? So we say critical number. So if I say critical number, I'll put the x value at x equals to 0. If I say critical point, I'll put both x and y value. So that is kind of difference, okay? So at this point, we do have a critical number. Let us assume this is our graph for x cube, okay? Now we need to analyze whether we have a local maxima, minima on this position or not. So for that, what do? So we analyze this point. So we analyze the graph of the function, right, around the critical number. Critical number is at x equals to 0. So let us take a value on left side and on the right side. So left side could be -1, right side could be +1. So that is in the interval from -infinity to 0, and 1 is in the interval from 0 to infinity. So if I write -1 here in our function, so in the derivative of the function, f of -1 will be equals to 3 times -1 squared, which is 3, which is positive, right? Positive means the tangent will be rising, correct? So positive means it is increasing in this interval. The derivative is increasing, correct? So derivative is positive means the function is increasing. So this is the value function is acting. Do you see that? Now if I substitute 1 in the derivative, I get 1 square, which is also 3, which is also positive. Do you see that? So that means the function is increasing after this interval also, right? Since the function keeps on increasing, it doesn't really decrease, so it cannot be a maximum. Do you see that part? So what we see here is that we'll learn later that the concavity changes, like it's concave down, concave up. We'll learn later. But at this stage, what we are learning is that on either side of the critical number, the function is increasing. It is not changing from increasing to decreasing or from decreasing to increasing. Therefore, there is no local maximum or minimum, right? So how to find whether the critical number corresponds to a local maximum minimum is to analyze the derivative itself. So either it should change from increasing to decreasing, right? Or it should change from decreasing to increasing, right? If it changes from increasing to decreasing, kind of like this, right? We have local maxima. Is that okay? If it changes from decreasing to increasing, we have local minima. You get the idea, correct? So that is how we can figure out whether at the critical point we do have a local maxima minima or not, right? So in following videos we'll take up some concrete examples and then see, or rather analyze the critical points and even sketch the graph of such functions. I hope that helps. Thank you and all the best.